Y se pone así y de preferencia colocarlo como así, cerca de la boca, pero no así. Y para nosotros, o para las preguntas de la audiencia, o para el chair, pues podemos usar este micrófono. Voy a decir y dejarles saber. Okay. A ver, les voy a preguntar si. Bueno, es que no escuchamos a ellos. Ok, bueno, ¿listo? Sí. Entonces, yo creo que ahora sí vamos a comenzar.
Okay. Is it working? Yeah, everyone hears. First, let me thank every one of you that you came. You did all this trip, and you are, I mean, we're not covering expenses. We're really happy that you managed to come here. So so first thing I want to do is to thank all of you to come. And the second thing I want to say is how all this started. And this started many years ago. It's not something that we just started last year. It's 3 years ago, something like that. 2 years ago, that Lydia, the wife of Volker, told me that Volker needs a conference for his 60th birthday, and it was a secret. No? She told me, "Don't tell Volker." So I was really trying to do it without Volker. He doesn't know, but at some point it was just impossible to do it because I had to talk to people, I had to do many things. So we were really, I was trying in many places to do it. The first option was Braunschweig, where is Volker, talk to people there. And it was a big effort to finally arrive into a specific thing, which is Merida, and to have all this settled. It was very difficult. So we had a lot of meetings and a lot of things with many of you. You remember probably 2 years ago we had the first meeting about that. I think so, no? Something like that. Yeah. But I'm very happy that we finally did it, and we arrived at this very nice conference with this with all these people. That's very interesting topics. Top, a very top conference in mathematical physics. So this is more or less the history of this. So we were actually thinking on there were many options. Not at the beginning. There was Oaxaca at some point, and it was changed to Merida in short notice last year, and also we were thinking Huatulco and other places. Yeah. And on the way we were thinking about all the things. I mean, this is something that is happening now, and we were kind of willing to try to do it more times. But not every year, but maybe every 3 years or something like that. Okay. So we're thinking on Huatulco, maybe in 3 years, and also to do some online seminars, something like that. And for that, we were organizing some little association on this. It's mathematical physics and analysis. That we have a web page of that, and for online seminars and maybe in other conference. And if you want to join, we will be very happy. We'll talk about that later. But if it's possible for you to join, that will be great. And you don't need to do anything. You have to write the names. There's no money involved. Everything is no money because nobody has money. But it's like that, yeah. So the other thing I want to say now is about the organization at CIMAT. This is a great job of Matthew. So I contacted Matthew December last year, and after that we were doing a lot of work, and he was really doing a great job. He made it possible for CIMAT, and also it was we had a lot of meetings now. So also I want to thank the director of CIMAT Merida, Jose Carlos Gomez Larriaga, and also they made it possible to have this here. And we have the other place that will be, that is in the Museo de la Luz. So in the Museo de la Luz we had to open also there, and also had to repeat all this stuff. I hope it's okay for you. We will open also again in the Museo de la Luz. And for the Museo de la Luz, we have we had to come a bit earlier as what is in the program. And this is important because this is a mistake that we did, that we start at 10, but we will start at 9:40, and it's very important that you are there at 9:40, please. No, because the director of the Museo de la Luz will be there, and we had to thank him, and so we didn't put it on the program, and I'm a bit ashamed of that. And Sergio, who is the guy that is taking care of that, he told me that we had to do that. And so please, 9:40, not 10, because we really need to open in the presence of the director of the Museo de la Luz. And we had to thank him, and he will give a little speech. Yeah. And so please, 9:40, please. The other thing I want to say is that tomorrow we have the excursion. It's a great thing that we managed to do. I'm really happy about it. I mean, we go to Uxmal, and then later to an hacienda, and we have the dinner there. It's all covered. I mean, you don't have to pay. We'll cover all the dinner for everyone, and also the entrance to the hacienda, and the visit to the cenote. This is all covered. This is Volker's grant, and so then this is what is in Germany. No, in Germany it's like that. When you have a birthday, you pay for the other ones. I mean, it's different in Mexico. In Mexico, you expect that everyone pays for you in your birthday. Or in Germany, you pay for everyone in your birthday. And this is what is happening now. Is Volker is paying for everyone for dinner. Yes. So this is a very nice place. And this we have to thank Yuridia Cortez. She was the one that made it possible. So it's she knows here, and she knows the people, and that was her idea, and she did all of that. Yeah. So thank you, Yuridia. She's part of the organizers. She's a local organizer, and so for the hotel, Benjamin already asked. Benjamin asked if it's possible to get a breakfast box in the hotel, and they say that is possible. So because we're leaving tomorrow at 6:30. 6:30. I mean, that's the official time. So then you can ask to the hotel to get the breakfast in a box, and they will give it to you at 6, maybe 6 or something in the morning. But you have to do it tonight. You have to tell them. Yeah, these are all the things. In any way, we will prepare. Actually, my wife will do it. Some sandwiches for you, and one sandwich. One. This is the idea. I mean, I had to check what else. Oh, this is happening now, honestly. But it's one. I mean, the idea is one sandwich, one apple, and some snacks. One snacks, and that's what you will get for tomorrow. It's not a lot, but but it's well, it's just for, because it will be a long day. But you can ask also on top of that for a breakfast box in the hotel. Yeah, yeah. Yeah. So there are some Mexican how you call it, snacks, and Mexican antojitos. It's around noon. As she said, we get that like tapas. So around noon you get that, and for breakfast, that's why you have the sandwiches or whatever you want. So what you do have to pay is for the entrance to Uxmal. This you have to cover yourself. Yeah, just you go to the entrance and you pay and enter and get into Uxmal. This you have to cover that. It's, I mean, as you know, it's very sunny. I mean, it's a lot of sun, and you need, if you have a hat, that will be good. You have a hat, or you can get it, and also some bread. Yeah, and I think that's it for me. I mean, just well, thank you very much again for coming. And now is Matthews is gonna talk about CMAT.
Thank you very much, Miguel, and thank you for all the work you've done for organizing, and also Volker Bach, and for all the work he's done, and the help also with the economic help for the excursion. It's really been a pleasure, and I also wanted to thank especially my wife, who helped design the name tags, and she's going to be the one picking up the food. You may have met her yesterday at the reception, so I'm very thankful to her, and thank you to Euredia for organizing the excursion tomorrow. So, and it's really a pleasure to meet all of you. I wish I could say that I was a mathematical physicist, but I wouldn't dare say that. I'm more of an analyst and representation theorist, harmonic analysis, but those fields have been related, intertwined ever since the days of Hermann Weyl. Hari Chandra, our most famous representation theorist, harmonic analyst, was first started working with Dirac and then moved over to the dark side of representation theory. So I'm looking forward to learn quite a bit, and hopefully we can have time for interesting conversations. So yes, I'm unfortunately our director, Jose Carlos Gomez, had to take a trip, so he's not here. So you're stuck with me for presenting CIMAT. CIMAT stands for Centro de Investigación en Matemáticas. This is our logo. It's a trefoil knot. CIMAT is an institution so I'm originally from the US, and there's not really an institution like it. I mean, they have these national labs there in the US, but there's none of them that does pure math research. And so CIMAT is similar to IMAS or IMATE in the UNAM, except that CIMAT depends directly from the federal government, from CECITI, which is the Science Secretariat. And so we have 4 missions. We do research, we do teaching of graduate students, because we have master's and doctoral programs. Here in Merida, so far we only have doctoral students, but there are master's degree programs, and next year we think we're going to get permission to extend the master's degree program to have master's students here. We also teach classes in the local universities and direct undergraduate theses there. So teaching, research, but also vinculación. I'm not sure exactly how to say that in English, but it means that you're basically offering services to industry or to government or to nonprofits, etc. Basically offering mathematical services. That because we have expertise as mathematicians, in addition to having the researchers, we also have staff that's dedicated to providing those services. And the last thing is what we call in Spanish divulgación, or public outreach. So we do a lot of, we invite schools to have their students come here and we give them talks. We have a lot of hands-on activities like Towers of Hanoi. Like we have this game which is called a Robotin, like a robot, and it teaches you how a computer works without having to actually have any electronic devices. And we also go out to schools. A few weeks ago, we went out to my doctoral student Volker went with us. We went to we went to the schools that were in Yohaktun, which is a small village about 50 minutes away from Tisimi, which is a small city that is about 2 or 3 hours away from here. So we do those 4 activities, and so I'm very thankful to the support that CIMAT has given me. They were able to pay for the transportation today and for the food that we'll be eating, and that was thanks to the director of CIMAT Merida that gave me that authorization. And so in fact, this is not the first time that we've done a conference here in Merida with IMAS and with Miguel Ballesteros. I think actually we met in 2017, when there was a previous conference back when the dinosaurs broke the earth before COVID. So it's a pleasure to meet all of you. And as you can tell, I tend to talk too much when somebody gives me a microphone, so I should probably leave it there. thank you so much to all of you. I'm really excited to see these folks and learn a lot. And yes, so I think I will pass the baton to Volker Bach.
Okay, good morning, everybody. I also want to say a few words directed to you. First of all, let me tell you how much I feel honored by your presence and the fact that most of you came, we're crossing an ocean to come here, or anyway through long distances to get to this conference and make it a top level event, as Miguel rightfully said in his speech 5 minutes ago. So I really feel honored, and I'm looking forward to this conference. And I would like to say a few words of thanks. So first of all, the first thanks go to the participants. You all came here and you prepared interesting talks presenting your results. So and the support for this conference is not very high. So you also look for the funding for your own participation. All this is much appreciated, I want to tell you. And then there's an organizing committee that has organized the conference here. And as Miguel said, it started already 3 years ago. Not that I had known it at that time, but some time ago I got to know this. And so I should first of all say how much I appreciate, Miguel, that you spent this big effort on and constant work on this event to happen. I really, really appreciate that. And let me emphasize that Miguel started as a postdoctoral fellow in my institute in 2010, so that's 16 years ago. And ever since, we built up a collaboration that is ongoing and in fact expanding and blooming. And most recently, we managed, and that was in some sense the most difficult part, we managed to establish a double degree program to have co-tutel theses, so doctoral theses that are advised by the two institutions together. And every one of you who has started this to try to get a collaboration with another university of this kind knows that this is a lot of work, and with no guarantee of success, but we did succeed. So I really appreciate this event here. Miguel, the main organizer, but there are other important organizers as well. Luis Silva is here. There's Diego Iniesta and Pedro Guillen, who have been crucial. There's Julien Ricot. These are the people from Mexico City that have been organizing this event. And then locally here, we have Aurelia. Now we finally meet in person after exchanging hundreds of WhatsApp messages. And Matthew Dawson is the same. I mean, he has visibly done all the work here for the conference to get going here in Merida, yesterday in the Museo de la Luz, today at CIMAT, and then also on Wednesday, Thursday and Friday in the Museo de la Luz. And it's always friendly and helpful, and I really appreciate that. So thank you very much. I'm sure it's going to be a great event. And then I would also want to say thanks to institutions that support this conference. So we have, first of all, the EMAS. There are two EMAS applied math institutes in the one, or maybe the branch of the same institute, formally speaking, the one in Mexico City and then the one here. And then there's also my university, TU Braunschweig, who supports this event by some funds. In fact, there is a little institution which kind of a spin-off, which allows also to pay expenses that the German law would not allow to be paid for otherwise. So that's very helpful. Yes, and then let me say a few remarks for the, maybe I just say a few words first about the association that you see here, the new logo of mathematical analysis and mathematical physics, that we want to launch here with this event. We are thinking of a series of online seminars and other formats, conferences. Miguel mentioned Oaxaca, maybe in 3 years from now. The intention is that we have a complementary association to what most of you know, the IAMP, and to have also opportunities for members of our community to present their work in a truly global audience online, and also from all countries, the contributions from all countries, and hopefully also covering areas that are not presented so much otherwise at the big conferences like ICMP of the IAMP. We'll see how it will be going. And you will be hearing about this during the next days again. So now, as for the dinner tomorrow, I would like to just organizationally make a remark. You have been sent a link to sign up for the tuna steak or the beef steak. And if you feel surprised by this, then I urge you to fill this form, online form out now. You just click on your choice and that's it basically. And because your area has to pass this information on to the hacienda today, this morning in fact. And then finally about the start on Wednesday. We should be there at 9:40. How do we make sure that this is going to happen? My proposal is we meet at 9:20. I mean, those that are at El Conquistador meet at 9:20 in front of the El Conquistador Hotel, just like we did this morning when we were waiting for the bus. And then we walk together to the Museo de la Luz. So then we have everybody there in time. Yeah, so finally, I think, Matthew, you are a mathematical physicist. You know, I looked at your abstract, and I would say your work is closely related to coherent states in mathematical physics. So you would be the first member to join the new association. Okay, so with this, I close, and I think we should start with the scientific program. Yes. Oh, okay, thanks. So there's more coffee. Okay, so then we can have a refill in our coffee cups now.
Hola, para los del IMAS, ¿me escuchan? ¿Me siguen escuchando bien?
Sí, sí, te estamos escuchando bien.
Y ya estoy compartiendo pantalla, ¿pueden ver?
Sí, ya, se puede ver bastante bien.
Gracias.
Sí, te escuchamos bien.
Gracias.
Just let me tell you something before. I mean, the conference is. I mean, there is a streaming, a live stream. It's streaming in the IMAS. IMAS is doing all this thing, and it's transmitted to many places. I mean, to YouTube, or I mean, and it's also to the channel, the YouTube channel of the IMAS of UNAM, and it will be recorded and saved in the YouTube channel at IMAS. That's in case that you want it like that. But I mean, if you don't want, please tell. I mean, you have to agree with that, and you have to sign something that you agree for that. Yeah, please. I mean, you will have these forms later, and if you don't want it, just tell us, because then we have to stop it, the transmission, the recording. Yes. Okay. So now the first speaker is Bernard Bru from the University of the Basque Country, Beckham, and he's going to talk about exchange interactions and corporate superconductivity. So.
try with this for the moment. Okay, I'm not used to have. I don't feel like I'm on TV. Okay, so I was saying that it's a collaboration with Antonio Delgado Pascual and Walter Schiapella, and Alan Ramar dos Santos. There is two papers, one is published in math and the other one in physics. And in fact, what I'm going to speak about, I mean, half of my talk will be a little bit less than half will be about math. And the other one will be about physics and about cuprate superconductivity, because I would imagine that not everybody knows exactly what is it about on a microscopic level. So that's the aim of my talk. So this is not. So if you like, you can put this. Okay. And this does not work, by the way. Oh, let me see if it was working before. But... Okay. Okay. So okay, I will go first. So first part is math. Second part is physics. So let's do in this way. And the first thing that I would like to explain a little bit. So I put exchange interaction. I mean, what I mean by exchange interaction? It's very easy. I will define at the beginning. What I mean of this kind of interaction, I mean some interaction where you have a particle which is destroyed and another particle which is created of different spaces. For example, a fermion is destroyed. For example, you have creation annihilation operator. A fermion is destroyed, and then a certain particle are created. So that's what I call exchange interaction. And this appears in various models on mathematical physics. The first one that I'm aware of is, for instance, the weakly perfect Bose gas, which was made by Bogolubov to do his microscopic theory of superfluidity. In this model derived by Bogolubov, you have these kind of things, and I've written explicitly what it is. And what is the two spaces and quote mark that I'm talking about in that case is particle inside the condensate is one species, and particle outside the condensate is another species, if you like. Consider it as two spaces. And this kind of interaction, I mean, that was a long time ago when I did my PhD thesis. I analyzed these kind of things, and this imply some depleted Bose-Einstein condensation. This term has a strong impact. These kind of things also appear also in the spin boson model, in the rotative wave approximation, and this kind of model makes it impossible to diagonalize such kind of model. So it also has this kind of interaction have a very strong impact on the physics of the model. More recently, there is one paper by Volker and Rauch showing that this kind of interaction. So in this case, here is particle which is inside the Fermi surface, which are destroyed, and create fermion outside the Fermi surface. And this kind of interaction makes impossible a relative bond with respect to the kinetic energy when you are in the Hartree-Fock state, so to say. So that's this kind of things appear, and this kind of interaction as always have a very big impact on your model. And one of the type of interaction that I'm going to speak about is of that form here, which is I would have a collection. I mean, my first species will be bosons, the other one will be a pair of fermions. So you have a boson which is destroyed and a pair of fermions which is created, and the other way around. So fermions are destroyed and a boson. So this is here. So that's one fermion, another fermion is destroyed and create a boson, and the other way around. And via a certain coupling constant, which is a certain function V. Everything that I'm going to speak about will be in two dimensions. not 3 or not 1. So you may ask why. I mean, I could do 4 other dimensions, but I skipped 2 dimensions because of cuprate superconductivity that I'm going to explain, and why this kind of interaction can be relevant for cuprate superconductivity. So that will be my second part of my talk. So for the time being, when you think you can just remind that I'm always in 2 dimensions, even if it's not really crucial for what I'm going to say. So I have a slide about, so everything is about second quantization, I mean, creation and annihilation operators. I suppose that everybody are familiar with that. So this slide is more or less useless. Only things that I could mention is I am in, again, I'm in 2 dimensions. So the one particle burst space is in Z2. The boson has no spin, and the fermion has spin up and spin down. Okay. So that's the only thing that, so that's fermionic Fock space and the bosonic, not Fock space, the fermionic one particle space and the bosonic one. Anyway, so so what is the model that I'm looking at for the moment would be a model with 2 spaces, bosons and fermion. So the first one as fermion. And basically, what I've written here, it's a formal model. Of course, I have an infinite sum. I am in Z2. I mean, everything is formal here. So this model, for the fermionic part, I have basically the Hubbard model. So it's a kinetic energy. This is just a kinetic energy, the second quantization of the kinetic energy. This is a Hubbard interaction. I could even ask also add an extended Hubbard interaction where so Nx is a particle number operators of fermion at lattice side X with spin, in this case with spin up, and in this case with spin down. As A is a fermionic annihilation, that is a fermionic creation, and B is the bosonic creation and bosonic annihilation. So in the fermionic guys, basically it's a Hubbard model. The bosonic one is just a quasi-free boson model. So there is no interaction. So here I use a model. I want this would be important for the end of the talk. I use a model which is invariant by 90 degrees. I don't want to break that. So everything, all functions that I put here, for example, this kind of function or that one, are always invariant at 90 degrees, because at the end the things which appear physically would not have this. There is a symmetry broken, and I don't want to have this in my model because otherwise you don't see the broken symmetry. So this is the quasi-free bosons. So Hubbard model basically here. And here the interaction is what I said before. It's this exchange interaction where a pair of fermions. So this is not one fermion. This is a pair of fermions. This is a definition of the C, and this is one boson. So a pair of fermion is destroyed and create this. The pair of fermion, if you would have z equal to 0. So this is just a function z equal to 0, and you don't have, I mean, just z equal to 0. It's a pair of fermion which sit on the same lattice side. But the pair of fermion could be on two lattice sides, and in fact that will turn out to be important for what I'm going to say later. Of course, if I want to analyze this model, for example, I don't know, I would like to know the ground state of, I mean, partition function. I mean, I'm not able to do it. I mean, already the Hubbard model is not solvable in that case. So I would like, but nevertheless, I would like to analyze the ground state property or the lowest energy property of that model. And to be able to do this, I will restrict that model I will simplify this formal model by saying that I have only 2 fermions and 1 boson. I look on that sector, 2 fermions, 1 boson. And the 2 fermions that I have are spin up, spin down, and I have 1 boson. In this case, if I reduce to that sector, I can explicitly analyze the spectrum and everything about that reduced model. And I would like to see what is the spectrum, if you have a bond state, what's going on for this, and what is the effect of this exchange interaction in terms of this reduced model. So this model, I mean, so that's the model with 2 fermions and 1 bosons. It's translation invariant. You can decompose that Hamiltonian in Fourier space in quasi-momenta on the lattice. So it mean something on a torus. So it's 2-dimensional. So it's torus square. You can decompose this one as for any quasi-momenta, you have a certain operators which depend on K. I put explicitly U was a Hubbard interaction here. It's not very important for the moment, but it can be for Kuprat superconductivity. And so I can decompose this Hamiltonian in fiber, and this Hamiltonian is on what is so this K represents the momenta of a pair, and each pair there is a relative momenta with each other. So this one is a fermionic part. This one is a bosonic part. The fermionic part is in L2 of the torus because there is still 1 degree of freedom, 1 momenta. And the other one, the boson, are no other degree of freedom, so it's just a complex number. And this term that you have here is coming from this exchange interaction. You replace a boson by a fermion and a fermion by a boson. So that's this one. So the first mathematical result that I can tell you is about what is the spectrum of that gas here. And so that is theorem here. So what do you have is something like that. You have let's say you have to fix a quasi-momenta. For example, one which is important will be 0 pi. I will explain why I take this one, but you take any k, it will be the same. So I take an alpha. And I look on the spectrum of the fiber Hamiltonian. So on the fiber Hamiltonian, there is a continuous spectrum, which is essential spectrum. I mean, which is this one given by this formula here. And below you have something here, which is my I of U K, which is a bond state for each yeah, and see this is the function of alpha. Alpha is here, so alpha, so that will be alpha 0 pi in this case. And you have a gap, so it's what you can prove. And everything, of course, depends on whether the exchange interaction. So the exchange interaction was something like sum over x and y, v x minus y, v x c y. Plus self-adjoint, and from V I use V star, which is a Fourier transform. Okay, so when I go to the quasi-momenta, I end up with the Fourier transform of the coupling constant. So this Fourier transform is what you have here, what you have here. And this is this eigenvalue which is unique, non-degenerate, and which has a certain eigenvectors. So that's so you can do your math, your mathematical analysis. You end up with this kind of things. One important property which also I can a little bit emphasize. I mean, 2 things I can emphasize. So this is dependent on the Hubbard interaction here. So that put U here, which is U. And this gap that you have here is not depending on U, so to say. I mean, you can make if U goes to plus infinity, it still remains. Why it is so? Because I allow to have a fermion, a pair of fermion in different lattice side. So if I do not allow to have 2 fermion, a pair of fermion in one lattice side, then the U destroys this pair, and which is not favorable. But when I allow to have pairs outside, in different lattice sides, the U does not make any effect anymore on the gap. And what is this bond state mean? It means that you have a pair of fermions which are glued via a boson. So it's a dress, it's a quasi-particle, it's a dress fermion pair, dressed with a bosonic field. And this pair of fermion is characterized by this function, which is the fermionic part of the eigenvalue, of the eigenfunction, I mean, the fermionic part. And this, if you look what is in the X space, this is exponentially localized. It means that the pair of fermion, which associated with the eigenvalue E, I mean, the wave function, the fermionic part is exponentially localized. So it's a small bowl, so to say, with two fermions which are close to each other. Okay, so you can, from this, if you know what's happened on the fiber, you can deduce what is for the original Hamiltonian, what is the spectrum. Yes. Mm-hmm.
So I mean, on the backward, you fix K to be alpha times 0.5.
Yes.
And in the theorem, you vary K, take the minimum over all K in torus.
Yes.
So is the minimum attained for these vectors?
Yes, the minimum is attained, I think. It's depend how you. Everything is depend how you choose V. It is minimum where this is maximum. V of V, the V, the Fourier transform of V has to be maximum. It's where it goes. And typically, what we will choose, it will be maximum in that 0 pi because of Kuprat property. So this is not really math. It's just because of the physics that I choose this particular thing. But for here, it does not matter. But the stronger is V, the stronger is this, the bigger is the effect. So you can deduce what is the spectrum of your Hamiltonian. You can deduce also the existence of a gap for the original Hamiltonian, knowing what you know for the fiber Hamiltonian, and you can deduce many things, the existence of a gap for the original Hamiltonian and so far. Okay, so you can also make, okay, maybe I do not have time really to present this, but you can also make the limit U, the Hubbard interaction going to plus infinity, see where it converges, and you can have some result. So now, I mean, because I do not want to have a lack of time, I mean, I go now to physics. So that's the math part. Okay, you say, yeah, okay, good. So what it is used for? So now I explain a Kuprat superconductivity, and I will explain why this model is relevant, could be relevant at least. So superconductivity, conventional superconductivity was found in 1911 with mercury a long time ago, and until so the first, microscopic theory which was breakthrough was a basis theory for conventional superconductors. So they find mercury, but then they find there is superconductor in aluminium, there is lead, and the temperatures to get this is of the order of 1 to 10 K always. So it's very small temperatures, very difficult to reach that one. And the theoretical explanation was basically the microscopic explanation was going from BCS, Borden-Copper-Schrieffer theory in 1957. But so the breakthrough about the birth of ITC superconductivity was in 86. And in 86, Bernard and Müller use a copper oxide, a Kuprat. It's a copper oxide made of copper and oxygen and other compound. And they make that, and they find a ITC superconductor. The other name is also ceramic. It's a ceramic. I mean, everything is the same kind of same names. And they find one which was a critical temperature which was 38. And that was a breakthrough because it was much higher than that, and it was already a Nobel Prize just a year later in experimental physics. And nowadays there is many. I mean, there have been many cuprat, different one, which was found, and the maximum temperatures is 165 at normal pressure. But for this in contrast with the conventional superconductor, there is no microscopic theory of cuprat, which is accepted by everybody. That's what Müller said, which is the Müller from this Nobel Prize here. And so this is this kind of question that I would like to discuss now. But to discuss that, let me give a little bit of more physics about what is cuprat, what cuprat is doing, what is this kind of material. So first of all, a cuprat, a copper oxide is at 0 temperatures. When you go to 0 temperature, it has two properties. It's antiferromagnetic and it's not insulator. It's not a metal, so there is no conduction. Then what Müller and Bernard did to get a superconductor. So this one is one all dop. I mean, this is a cuprat, and so X, which you get here, it's a doping. So when X is equal to 0, your cuprat is so this corresponds to X, which is A. So this you go down in temperature. This is a temperature. So you go down, and then you have an antiferromagnetic phase and more insulator. So what's happened if you start to dope it? So for example, this compound adds some hole. So adding some hole, if you have a more insulator, you have basically an integer number of fermions in each lattice site. I mean, and you broke these things. So what's going on is when you dope it, the antiferromagnetic rapidly decreases, the critical temperature rapidly decreases, and then you have the appearance of a superconducting phases, depending on the doping. With the best doping is air, which is highest superconductivity. And then there is another critical temperature, which is a pseudo-gate regime that I will come back again to this. So it's like a semiconductor. You dope it, and doping it, you change drastically the behavior of your compound. One thing that I should also mention, I speak about integer number of particles in each lattice site, and I was also in the first part of my talk, I was speaking about 2D. So what is 2D here? So what is shown is that so this is one, for example, one cuprat is what is the structures of one cuprat. What is all cuprat has in common is that they have always as layer of copper and oxygen. So this layer that you see in orange and green, it's copper and oxygen, and they all have this layer, two-dimensional layer. And this is my 2D, because the superconductor, the transport is shown experimentally to take place in this two-dimensional layer made of copper and oxygen. And there is something which now is experimentally demonstrated, which is the existence of polaron. So why Müller and Bernard find this cuprat as a candidate to make superconductivity? It's because he was studying a compound with a Jahn-Teller effect. And the Jahn-Teller effect, one which has a strong effect, is the copper. So what is Jahn-Teller effect? Is you have an electronic structures of the copper, which is symmetric. The ground state is symmetric but degenerated, and the degeneracy make it unstable. And then there is a second, a broken symmetry, which make a distortion of the state. And then there is a Jahn-Teller effect. So it's Jahn-Teller effect means that there is a distortion of the geometric configuration of your atom. In this case, this is a copper, and is known for that. And that's why they found this, because they wanted to use this It's because of this. So that was the aim. And so what it happened? So when an electron, so the electron are moved, or the electron are all the fermionic particle. In fact, it's all. It's not electron. They move in this two-dimensional layer, and typically it is experimentally shown that they move inside the oxygen, not in copper, inside the oxygen. But on the other hand, so this is the oxygen, this is the copper. On the other hand, sometimes they go to the copper, and they are trapped with this Jahn-Teller effect, produce a deformation of the lattice, and this it form a quasi-particle which is called a polaron. And they do not, so that's the concept of polaron. So now I speak about bipolaron. So it's antiferromagnetic. So the polaron, when you have it's favorable to have two holes which are trapped at the same times, making not a polaron but bipolaron. So this is there is a geometric deformation here, polaron here and a polaron here, and they are connected via the oxygen. And this is favorable because you can add this with a spin up and then a spin down, and it is shown experimentally that even beyond, with doping, there is antiferromagnetic correlation. So they would like to have always to have spin up, spin down, spin up, spin down. They don't want to have one spin up which broke this, so it's favorable to always have up and down. So in this case, the best configuration to do that is not to have one polaron, but have a bipolaron. So that's, and they are typically linked with one ligand, which is this oxygen. So one is going here, and one is in here. One is linked, in fact, yeah. One is here, and the other one in here. And what is the exchange interaction that I'm talking about is when you release the bipolaron. Once the bipolaron is destroyed, then the two all come back to oxygen and can participate to the transport. So that's my exchange interaction. Yeah. Yeah, because it's if you don't have any doping, you don't have any extra electron. So if everything's sick, it's not, and nobody moves. But if you have one more, that it start to make to start to want to move, and it doesn't know where is this place, and that starts a business. So now I repeat a little bit what yes. It's for example here, SR, I forgot what it is. It's like in semiconductor, you put an element which add either more electron, it's electron dop, or attract one electron, so it's a all dop. So for example, I forgot what is the name in English. For example, in this case, this is SR, but it's I don't know if you know what is this atomic serenium. No, I forgot what is the name. Or strontium. See, this is strontium, for example, in that case. But there is many examples. It does not depend on what is the doping really. This atomic is not really relevant for. Okay, so as I said, the group only appear in oxygen. Bipolaron are related to the strong Jahn-Teller effect of copper atom. The bipolaron are zero total spin because it's antiferromagnetic, so it doesn't want to have two all or two fermions which are spin up. No, they want to have always antiferromagnetic correlation, so up and down. And other type of polaric particular disadvantage. And one thing that I did not say in that slide is that there is experimental evidence of a short lifetime of polaron. So if you would be trapped and stay forever, then nobody participates to the transport. But the point is these polaron does not have a long lifetime. So sometimes you are trapped, you make a bipolaron, but then you are released. So this is experimentally shown that they have a short lifetime. And okay, so this does not work anymore. I forgot what is in the next slide. Okay.
Oh, I know what I have moved the mouse.
Okay, and then it decreased. Yeah. Well, no, it's fine. Yeah, okay, so so now different comments. So in the microscopic theories that you have in Kuprat, usually they don't. Most of them does not deal with bipolar ionic particles. They avoid this. They have typically a purely electromagnetic. They use the antiferromagnetic phases as something key, and also the fermion. But they separate this to the diatomic and to the atom particle, which makes a lattice. For them, it's not important. And there is others. So this is the large community, the biggest one is they are doing this. So this is with TG model. I don't know, maybe RFB resonant valence bond model. They use this, and they don't speak about polar ionic particles. So there is a very small community which takes seriously the bipolar ionic cases, but they used to think about that the quantum transport is made of bipolar ions. So the bipolar are moving, and this is what makes the transport. And then there is a Bose-Einstein, for example, Bose-Einstein condensation of bipolar ion, which makes my superconductor. So there is a small part, very a small one, community which doing this. The problem with that is that the effective mass of bipolar ion is supposed to be large. It makes unlikely that they are participating to the quantum transport. Also, the effective mass of the particle of the charge carrier are not so small, are not so big, 3 or 4 times the electronic mass, whereas the bipolar mass, for example, it is estimated 700. And so the bipolar ionic particle, it does not seem to be a very good candidate as a charge carrier. They also show an experiment that there is a different kind of experiment that there is in fact 2 kinds of particles. There is a bipolar ionic particle and also charge carrier which are not. So they show that experimentally. So this is another endpoint. And what we do is we use this exchange interaction to define the boson that I was talking about was a bipolar ion, and the pair of particles that I was talking about is the particle of the charge carrier, which are released by the bipolar ion. So that's my interpretation of the first model that I have before. So what I say, so there is no conferencia microscopy. The existence typically of polytype is neglected. One thing which makes them neglected this is one, for example, experiment which was I don't know, more than 20 years ago. They show that if you have a effect of the lattice, a way to show it, you make another isotope. So for example, you take the oxygen and you replace this oxygen with another isotope. And the mass of oxygen will change the property of the lattice and change the property of the bipolar ion, and so it's a way to see if. And this isotope effect was not at critical temperatures for Kuprat at the beginning. But then so they start thinking that we don't need this bipolar ionic to explain the space. Something it's more related to the antiferromagnetic phases. But this bipolar ionic fact is strongly emphasized in further experiment because they have a strong impact on 2 things, in particular on the pseudo-gap regime that I will explain, which is really crucial in that Kuprat. In our case, so bipolar ion was always there, but there is a big communities that don't want to do this. So as I said, our one guess is to use this to explain the functioning of this. this external interaction. And another ingredient which is really important, that's why there is this U, these cuprates are Mott insulator. See, if they are Mott insulator, it's a strong indication that there is a strong Hubbard repulsion. So Hubbard repulsion should not be neglected. You should not say, I have everything quasi-free and I tell you, you need to take into account the Hubbard repulsion. So that's something that you cannot avoid. Okay, oops. There is one thing that you can ask. So now what I'm going to explain and try to convince you that you can have quantitative estimate for that. With the model that I presented before, I can quantitatively give a number in terms of correlation function and so on. So I would like to explain you how I prescribe all my function. For example, you can ask, what is this U or what is this V looks like? It could be anything. So one thing that you have in the property of cuprat is phononic property. The cuprat, so the formation of bipolar ions, everything has to do with also with phonon, existence of phonon. And the phononic of property of cuprat are particular. They have some two quasi you can analyze experimentally, and there is two singular behaviors for two different kind of quasi-momenta, which is quasi-momenta 0 pi pi 0 or 0 plus or minus pi over 2, and the other one here. For this specific value of k, you have an anomaly in terms of. So what's going on? So one and the anomaly for this and that are different. For this one, this anomaly is due to it's a softening of the phonic energy. It means that the phonic energy, the effective, how do you say? Yeah, the spectral energy, I mean the energy of the phonon with respect to k, decrease a lot when you reach 0 pi. It's more or less constant, but then it decreases a lot. So for 0 pi, something happens. And the other one is if you look on response in terms of response, you see that for this mode k, the response is not sharp. He has a broad response in terms of phonic excitation. This one is well reproduced, so you can with some density functional theory use behind as they try to reproduce numerically this anomaly. These are able to do it, and these are not able to do it. And once they are able to reproduce this by density functional theory, and this density functional theory does not take into account the existence of polarionic particles. And so that suggests that if this reproduces this, it means that there is no polarionic particle, because this is not included in their modelization, whereas this one is a good candidate of this. Another argument to that is the fact that I said there is a pseudo gap temperature. So there is something which is here. This is the doping. This is I don't know LRSRX2 minus X. This is a certain cuprat CuO. I forgot the number here. And then the pseudo gap. There is a pseudo gap temperature. This is temperature, and then there is air. There is a semiconductor, supraconductor. X is a doping here. And X is a doping. And then there is a pseudo gap temperature. I haven't said what is this. It means that on some quasi-momenta there is a gap. So it may be for quasi-momenta k equals 0 is no gap, but for quasi-momenta k equal in particular 0 p there is a gap. And it's shown experimentally that the gap is for 0 pi. It corresponds to this EK, so for a special case with a gap, and maybe for k equals 0, the Fourier transform of V is 0, and then there is no gap. And so what we shows, which shows a function V, which is peak around this this mode. This is a natural candidate that we do. So a function will speak. So this is an explicit function. So this is pi 0 minus pi 0 and so on. So it speaks only on 0 pi with a certain. It's not only a Dirac. It's and that's that one thing. And so the model. So let's come back to the model. So the model, for example, I can. Let me simplify a little bit. So this is a Hubbard model, I recall. The other one is a quasi-free bosons here. So just no interaction. The interaction is the exchange interaction is of this form, as in all my talk. And then I have I simplify my pair of electrons by putting only. So it's a pair for all with distance 1 maximum, because if the bipolar ion is released, they share the same oxygen, and so when they move, they cannot move far away than a distance of 1. So we just keep this as equal to 1. And if you do this model, what I've presented before, you have explicitly, well, okay, this theorem, I mean, you don't even need to read this. So only a message that I put here is that if you use this model, you have an explicit expression in terms of integral. So you can run it on the computer. You want to know what is this function on the computer. So everything can be for that model can be done. So okay, here there is a condition which can be done for the existence or not of this EK, and you can. Well, the only message is you can do it with a computer now. And to do it for a computer, if I would like, I need to know all my parameters. So I have already said that this function V is peak for 0 pi or pi 0. But now, what is the strength? What is my Hubbard repulsion? What is my kinetic energy? I have many other parameters to fix. And also V, I know it's peak at 0 pi, but what is its strength? It could be big, but very small, or very big. So it's what we have to think of. So there's another thing which is that I haven't mentioned, which is also important to mention for Kuprat. Maybe it's a lot of information for physics, but the Kuprat has also a very particular property with respect to conventional superconductors. What is this? So you have a macroscopic superconducting state, and in conventional superconductors, typically this macroscopic wave, so to say, is isometric. It's a so-called S wave. It's isometric with all. But for Kuprat, there is a D wave part, a significant D wave part. D wave part means that the wave function, when we make 90 degrees rotation, you get a minus sign. And so if you want to explain Kuprat, you need to have this kind of symmetry. And as you mentioned in your first question about this U, this symmetry, it's related to that. I have a model which apparently is completely isometric. I haven't done nothing by hand here. And to know this, so what we are going to do, we are going to. So you have a certain U K. This is a bound state at each K. I take K. I look at 0 pi, which is the one of interest. Then for this one, he has a certain eigenvalue. So I forgot what is maybe it's UK. It's again function, again vector. So this is bosonic part. It's a number, and this is the L2 function. L2 of the torus. This is the fermionic part, which describes the pair, or the pair is look like at moment OK, which is 0 pi. In this function, I will. So what we will do, we will compute this, and we try to compute the symmetry of that function. And this function can be decomposed in S wave, D wave, P wave. There is an easy way to decompose this in 3 components. And so then you look if this has a S wave or D wave, or what is the proportion of S, a D wave or P wave. P wave means that you are symmetric under, when you make a rotation by pi, you get -1. D is when you make a rotation by pi over 2. And S is any rotation between 0, pi over 2, pi, 3 pi over 2, 0 is isometric. This is S. And in Kuprat, so this is also something which is neglected in many microscopic theory, is they neglect a lot that they think that it's 100% D wave. But this is with an experimenter says it is not. I mean, maybe I don't know what time is it. Maybe I'm running out of time. But it's not 100%, and so it's what I'm going to show it. So let me give you shortly what is. So you have to fix this epsilon, hopping amplitude of all. So you have h bar, you have the lattice spacing, you have the effective mass, so you can define what is epsilon. This, the hopping amplitude of bipolar ion, it's the same. You have the effective mass, the lattice spacing, you can define this. What is U? U is when you go from O minus minus, it's all, and when you add a all. If you add, so this is it's called electronic affinity of oxygen. It gives you a number. The amplitude K of the exchange interaction, this is the most difficult to fix. We fix it by knowing that there is a paper in Nature in 2016 which says that 90% of the charge carrier of the all doping does not participate to the charge carrier. So it does not participate, that means they are bipolar. So we run our model in such a way that, so what is the proportion of bipolar? So you have this, you look on the proportion of 1 divided by the full norm. This is the proportion of bipolar. You think that it should be 90%. That gives you a certain number, and you look if it's coherent. Of course, if you find, I don't know, 1 billion of electrovolts, you say, and the other one has 1 electrovolt, you say there is something bizarre here. But everything it's much smaller than it's a little bit bigger than the hopping amplitude in terms of electrovolts, but smaller than the Hubbard repulsion, but on the same order. And doing this, what we find is the following. So we find this. So what we find is, we find 60% of S wave, 83% of D wave, 0% of P wave. But this is not numerics, it's just by mathematical argument. X1 data mean 20-25%, D wave it's 75-80, but these are crude estimates, and here it's 0%. We found the absolute temperatures, so you can analyze what is the value of this. This is the binding energy of your value. So in terms of Kelvin, it's 1250 K, which is coherent with the experimental data, which is there. I mean, it's normal that the binding energy is much higher than it's typically with diatomic molecules. The binding energy and the dissociation temperatures are not the same. They are a few order less. So this is what we find is completely coherent. And the thing the more interesting is the coherent length. The coherent length, the prediction that we find is 1.6 in one direction, it's anisotropic, and 2.1 nanometer in the other one. And the experimental data is between 1 and 3.8. In fact, for this one, a certain doping, optimal doping is 1.6, and there is another Kuprat, which is this one for doping, which is not completely optimal, which gives you 2.1, exactly the same number, but okay. And this is also very coherent because in conventional superconductors, the coherence length is very big. It's a few hundred nanometers, which we do not find here. And this has to be related with what I presented the theorem that these are exponentially localized. I have a theorem that says that the pair, the wave function, is exponentially localized, so it should not be big. It's exponentially localized. So that's what we find here. So I think I don't know. I mean, I have no clock. I have no. So I close here. I mean, there is so that give you a, I don't know, an idea of a proposal for microscopic theory of cupra, which need to be developed, I would say. Okay, thank you very much for your attention.
Thank you. Do you have questions?
Okay, 3 minutes.
Thank you. Thank you very much, Jean-Bernard, for this beautiful presentation and these very interesting results. So my question is, the function V, the potential, is obviously of great importance for the quantitative predictions. And but this is some effective potential that you would derive from, let's say, microscopic model. You started to present a microscopic model in the beginning with the Hubbard interaction and so forth. So is there a way to estimate these functions for the effective one particle model that you actually analyze by, for example, using Bach projection method?
Yeah, I mean, we haven't, I mean, it's one thing that I haven't said here. This what we use, we don't analyze a collective phenomena because it's not many body. So first of all, the first remark, so I don't know exactly how you derive this for many body model. We are analyzing, in fact, what we analyze, it's not really the superconductor, it's a pseudo-Gauss regime. So the probability is that two electrons get dressed locally. And so this what we analyze, it's more air than air. And for the many body problem, I don't know if you have an effective how you would derive this effective interaction precisely. I have an idea how to do the many body, but not related to deriving this function V as an effective.
So it's future research. It's future research.
Yeah, it is.
Do you have other questions?
I would like to make a remark if there's no other question. I don't want to, so to say, occupy the discussion. But I think actually that this is very good work on a very important problem that sort of has been forgotten over the many years. When I started my PhD myself, which is in 1989, then that has been, so to say, the hot topic in theoretical physics, and everybody was working on this. And then it turned out to be a very hard problem, and which could not be solved. And even worse, the solution proposals made in the theoretical physics were contradicting each other and were very controversial. And this led to a disagreement of everybody with everybody else, sort of. And even worse, the Pope, so to say, at that time of solid state physics, Phil Anderson, also changed his mind over the years that in the beginning, the order parameter would be S wave, and then after 10 years, he says it's D wave, of course. And so I think it's very important to get an answer, and if this could be found in mathematical physics, that would really be fantastic.
Right. Thank you. Yeah, I mean, what we have seen is I don't speak about mathematical physics. In theoretical physics, it doesn't seem that there was a lot of some kind of decrease of interest, or maybe they found it's too old and they have more fancy things to solve it, and then it's and everything is like crystallized. So community are crystallized, and it's a little bit the impression that they do what they used to do, and so it's a little bit the impression that we got from looking at it from new eyes. I don't know, for fresh eyes, at least.
So do you have another questions? There's no more questions. So let's thank again the speaker.